morning. A warm welcome to the Humanist Community in Silicon Valley Sunday Forum to those joining us this morning. My name is Ray Sunby, President of the Humanist Community. The Humanist Community is a chapter of the American Humanist Association. Humanism is a secular and reality-based philosophy of life that affirms our ability and responsibility to lead ethical lives of personal fulfillment that aspire to the greater good. We value freedom, health, happiness, fairness, compassion, and using science and reason to acquire and apply knowledge. If these words describe your thinking, we invite you to become a member of the Humanist Community if you have not yet done so. A special welcome to those who are with us for the first time. We invite you to continue listening to our weekly forums and other events. Please aid us in continuing to present these forums by donating to the Humanist Community. Membership forms, a list of upcoming events, information about donating to the Humanist Community, and other information can be found on our website, www.humanists.org.
Okay, good morning. My name is Alex Havasi. I'm Vice President of the Humanist Community. Okay, today, Sudanshu Suds Jain will discuss geoengineering to avert climate catastrophe. He's been working for almost 10 years on a scheme to make marine boundary layer clouds brighter by spraying purified seawater into the air. Suds holds a BSEE and MSEE degree from MIT and designed integrated circuits for 25 years. In 2008, he decided that the climate crisis was more important, and he retired to become a volunteer. He's active with the Citizens Climate Lobby, which advocates a carbon tax. He has taught a weekly climate change science class to middle school students. And he's been working with the Silver Lining Marine Cloud Brightening team since 2012. He also currently serves on the Santa Clara City Council. Suds? You're up, and you're muted.
Thank you very much, Alex. I'm going to share my screen now, and I'm going to dive into the presentation. I do have two monitors, so I should be able to monitor the chat. I guess maybe Alex could interrupt me if there is something that I missed. But I'm going to share my screen here. Okay, can you guys see my presentation? Yes. Okay, very good.
Yeah.
Okay. Come on. There we go. Okay. So as Alex had said, I've been working on this since about 2012 when I met Armand Neukermans, and I'll talk about him later, but he's quite inspiring. He's really the mastermind behind this effort that I'm working on. All right, so here's an overview of what I'm going to talk about. First, I'm going to talk about sort of the urgency to address climate change and the IPCC. That's the Intergovernmental Panel on Climate Change. That's a UN body. And their warnings, they've just declared code red for humanity. A little bit about what geoengineering is, various schemes for doing geoengineering, experimental work on marine cloud brightening, which is what I'm working on, then some governance and funding issues. So I actually spoke to the humanist community in 2016, but mostly on marine cloud brightening. So today I'm expanding it to talk about a few other efforts out there. This chart here tracks the average global temperature from 1850, which is basically when we started having thermometers, so we could start tracking this stuff. And what you notice is that basically since the 60s, climate has been increasing dramatically. And what you see here in the upper right is that the last 6 years have been the hottest 6 years on record since we've been keeping these temperature records. So that's pretty scary. And this is about the IPCC warning. And what it says is that uh, human actions are causing dangerous disruption, and the window to secure a livable future is closing. There is only a narrow chance left of avoiding its worst ravages, is from the IPCC report. All right. And in California, as you know, we have wildfires and we have droughts. And this editorial from the Mercury News in March said, climate change isn't a problem for the future, it's here. And California hasn't remotely prepared to deal with the consequences. And as you know, that we're in this record drought right now. Okay. So we actually had some very disturbing news, two pieces of news in March. One was there's an area of the Arctic called the Vostok where they've been doing these ice cores. They drill down into the ice. It's been building up for 1 million years, and the snow never melts, so the ice has just been accumulating. So if we drill down there and we get ice cores, we can actually see what the temperature and the CO2 concentrations were up to 1 million years ago, because the snow has never melted. Well, now that area has gone above freezing, so parts of it are starting to melt. So in fact, in that area, parts of the Antarctic ice sheet were 50 to 90 degrees Fahrenheit above normal for 30 days. And it broke the previous monthly record by 27 degrees Fahrenheit. And then we're in the 6th great bleaching event of the Great Barrier Reef. This is when the ocean temperatures get really hot, and then the coral animal basically gets agitated and kicks the algae, the symbiotic algae, which feeds it, out. And so then the coral gets bleached because the colorful algae are gone. So just trying to make sure that I'm monitoring questions. All right. So in Scientific American in 2021, last year, said we basically have about 11 years left. We would use up 89% of our remaining 1.5 degree carbon budget by 2030. So that's basically 9 years. And 39% of the 2-degree budget by 2030. So, you know, everyone's issuing these really dire warnings. So now the interesting thing is that, you know, Scientific American is saying we only have about 11 years left to basically get off of carbon generating fossil fuels. And the problem is with this Ukraine war, there's a shortage of oil, and oil prices are really high, gas prices are high, and everyone's complaining, and everyone's like, let's drill more, we need to drill more. And I like to say that, you know, for my Ford Focus electric, I'm paying effectively $1.20 a gallon for my transportation, versus $6 a gallon for people that are burning gas. So we actually need to be burning less fossil fuels. And if we do it properly, we can save people money. So, all right. So there are various techniques for geoengineering. There was a PBS Nova episode that aired in 2020. Our team is actually is one of the featured teams in this Nova episode. It's available for free. The link is here at the bottom. But it was about, can we cool the planet? You know, all of the CO2 that we've emitted has basically created a blanket that's trapping the heat. And we call it the greenhouse effect because it's exactly the same physics as why greenhouses are warm in the wintertime without any, you know, heater inside. There's no gas heater or electric heater in there. Just the physics of it is the visible light gets through the glass. When it hits the surfaces, it turns to infrared. The infrared can't get back through the glass. And that's what's happening with our planet is the CO2 is like a piece of glass that we've extended over the planet that's creating a greenhouse. So, so we have all this extra trapped heat that is, this energy is actually amping up the hydrological cycle, the wind cycles, all of the processes on the planet and causing these tornadoes that we're seeing, all kinds of things. So somehow we have to actually get rid of that extra heat. So this is why we call it, can we cool the planet? All right. So we actually have evidence of cooling the planet. This is Mount Pinatubo from a satellite, and you can see this huge plume right here in the middle. Can you guys see my cursor? Yeah, okay. So you can see this big plume that's actually injecting 17 million tons of sulfur into the stratosphere. And so it's pretty dramatic to see this plume coming out of here. And what we actually see is you can look at the radiation, the transmitted solar radiation that's hitting the planet. And you can see that less sunlight is basically hitting the planet when we have these big volcanoes. So in, so Pinatubo here, you can see that you got quite a bit of dimming here from the from basically this 17 million tons of sulfur that were injected into the stratosphere. And here you can actually see that we've actually had volcanic winters due to Pinatubo and Tambora. Tambora is a bigger, it had a volcanic explosivity index of 7. You can see here that the explosivity index of Pinatubo was 6, and this 1982 volcano Chichon was only 5. But here, this is Pinatubo here, and so you can see the temperature change in various parts of the planet, the stratosphere. What it did, you have model and observations, the troposphere, and then the surface of the planet. But you see cooling of different levels, anywhere down to 0.6 degrees Celsius versus 0.4 degrees up to 0.6 at the surface. So, but Tambora, which was a bigger volcano, it actually created a year without a summer in Europe in 1816. And actually, there were frosts in the middle of the summer in New York State, and there were famines and food riots, and about 100,000 Irish perished due to famines at that time. So this just shows you the effect of what the stratospheric aerosol, this sulfur in the stratosphere, can do. All right. So, so what is geoengineering? So it's actually a deliberate intervention in the climate system, and it's we think it's a mechanism of last resort. The first thing you need to do is stop emitting carbon, and then figure out a way to get that carbon out of the atmosphere. We're at about 418 parts per million. Pre-industrial, we were at 290 parts per million. So we're really like 30 to 40% more than what we were pre-industrial. So we need to stop putting more carbon in the air, and then we got to figure out a way to get it out. And so there are, of these geoengineering schemes, some are ways to get carbon out of the atmosphere, and others are the way to get heat out of the atmosphere. So there's various schemes. Ocean fertilization. There are areas of the ocean where they don't have enough minerals, so the plankton are kind of starving. So there's ways to add minerals back, and that will through photosynthesis, suck more CO2 out of the atmosphere. I'll talk about that. Afforestation, that means planting more trees or encouraging more kelp to basically absorb sunlight and carbon dioxide. There's direct air capture, which are machines that we create that basically filter CO2 out of the air and then somehow figure out a way to capture that. There's enhanced rock weatherization. There's certain rocks like basalt. If you grind them up and you spread them out, they actually will absorb through chemical processes CO2. Okay. There's a team here in the Bay Area called the ICE 911 project, and they have developed these tiny 35 micron spheres that are hollow that float, and they're highly reflective. So you could enhance the reflection of sunlight. Okay, there's people working on enhanced photosynthesis. Plants are only like 1 to 3% efficient at capturing sunlight, whereas photocells are up to 25% efficient. So there's room for making plants more effective, but that's genetic modification. And something that's scary to me and a lot of people. And then there's solar radiation management, which is what I'm going to talk about. It's stratospheric aerosols and marine cloud brightening. All right. So there's a number of books. Some are nonfiction, some are fiction. I don't know if you have read Kim Stanley Robinson. He's famous for his Mars trilogy, Red Mars, which is about what you'd have to do to geoengineer Mars to make it livable for humans. Since it has no atmosphere, the cosmic radiation, the UV radiation is toxic to humans. So how do you engineer the planet to get water and to get protected from the intense sun radiation? There's a great book called A Planet Remade, talking about various geoengineering techniques. Our project is actually in that book too. Elizabeth Colbert is a fabulous author. She wrote The Sixth Extinction, but more recently she's written a book, Under a White Sky, which talks about breeding of these corals to make them more heat resistant, and then also brightening the sky to reflect sunlight. And Kim Stanley Robinson, he's also now talking about in this novel how to manage global warming, climate change through a ministry that would manage the planet. Okay. The National Academies of Science is now starting to take this seriously. They just had a publication called Reflecting Sunlight and recommendations for solar geoengineering research and research governance. Governance is a really key part of this. I'll talk about it, but if you screw it up, you could cause famines, or you could cause floods or droughts. So you got to get it right, and you got to get people to buy in. The IPCC, the Intergovernmental Panel on Climate Change, they had their assessment report number 6 that came out last year, and they talk about solar radiation management, which is reflecting sunlight back. Stratospheric aerosol injection, which is kind of what the volcanoes do. Marine cloud brightening, which is the project that I've been working on. Cirrus thinning. I was talking about those wispy clouds earlier that actually trap heat, and so try to get rid of those wispy clouds that are super high in the atmosphere. Surface albedo modification, that's like those little ICE 911 microspheres. For solar radiation management, there are, the ICE microspheres are made out of sand. They're made out of silicates. So they're very benign. They're basically sand. They're actually used in some manufacturing processes, but these, and I'll show you a picture of them, but they're basically just silicate. So, all right. So for solar radiation management, there are sort of two places where sunlight can be reflected. One is way up in the stratosphere, where you put in these sulfates, where volcanoes have been injecting these sulfates, and then you get this scattering of light. And then if you have these lower clouds, you can scatter light off of those. So, all right. So, geoengineering is kind of scary, but we've actually been doing it since 1946. And it's called cloud seeding. And in fact, because we're in these mega droughts now, all 8 states have really ramped up their cloud seeding efforts. Colorado, Utah, Wyoming, Nevada, California, Idaho, New Mexico, and Arizona. And Idaho Power, they operate 26 cloud seeding generators, which are injecting silver iodide crystals into the air. The first cloud seeding was actually done at GE in upstate New York, where they dumped dry ice into the atmosphere and they saw increased precipitation. So, but this has become commonplace and people don't seem to worry too much about this. So here's another example of unintentional geoengineering. All of the fossil fuels that we burn are emitting these aerosols into the air that are actually will seed clouds and affect rainfall patterns. But we've been doing that for a long time and doesn't seem to be a problem. I mean, it is a problem because it kills 4.2 million people annually, but in terms of calling it geoengineering, doesn't seem to be a problem. So these air pollution sources vary in different parts of the world. So here you'll see in the East Coast or the Midwest, it's mostly sulfur from burning coal. Okay, and then off the coast of California, it's mostly sea-generated aerosols. This is from sea salt spray and from blue-green algae emitting these dimethyl sulfides. So you have different sources. They vary all over the earth. Okay. Whoops. So what happens is that all of this emission of this unintentional aerosols, these are very small particles in the air, is estimated to cool the planet actually by between 0.5 degree and 1.5 degrees Celsius. So we're already getting this cooling effect. And the odd thing is, as we try to clean up the air, as we try to limit sulfur emissions from diesel power plants and coal plants, we actually could be warming the planet or increasing the amount of what's called radiative forcing. So this is radiative forcing. This talks about the different contributors to the heating of the planet. And the forcing is in watts per square meter. So every square meter, how much extra energy is being absorbed by the planet. Okay. And so CO2 here adds, and these little bars here are uncertainty bars. So CO2 adds like almost 2 watts per square meter. Okay. Then other greenhouse gases add like methane and nitrous oxides. They add some warming. Okay. And then ozone adds some heat, but it could be negative too. So in the stratosphere versus ozone in the stratosphere versus the troposphere. Stratosphere is the higher level layer, and the troposphere is basically where we live. So you get warming from ozone in the troposphere and cooling of ozone in the stratosphere. Okay, and then surface albedo, this is like chopping down, desertifying land, chopping down rainforests. From land use, you get different things. But this is what I wanted to focus on, is the aerosol cloud interactions. This is that pollution that I talked about up here. It's negative. It actually cools the planet. But look at how big the uncertainty bar is. We really don't know exactly how much it is. And it's got even a much larger uncertainty bar than CO2. And this is where we need a lot of research. We have to narrow these bars of uncertainty so that we really know what's happening. And that's where we're advocating for a lot of research in this aerosols. Any questions? Okay. So the Keeling curve is basically in the late 50s. We installed a CO2 monitoring station on the top of Mauna Loa in Hawaii. And it's been tracking the CO2 levels. So it's so remote that it's not affected by, people driving their cars and any power plants or anything. So it's remote. And it's been just recording this steady increase in the CO2 concentrations on the planet. And you see every year there's a little up and down. And interestingly enough, there's more land mass and more vegetation in the northern hemisphere. So in the growing season, basically from May until September, the CO2 concentrations actually drop on the planet because all of these plants are sucking up CO2. So it's kind of interesting. Okay, so this is the first geoengineering project that I talked about. This is actually to reduce the amount of CO2 in the atmosphere. So there are these vast areas of the ocean that are lacking in micronutrients or nutrients like iron or phosphorus. And so these people have hypothesized that if you then sprinkle these nutrients out, you can get all of this plankton blooms, and that would take up the CO2. And then when those phytoplankton die, that mass would then filter down to the bottom of the ocean and sequester that CO2. So they did a number of field experiments. In fact, some of them were rogue. This one in 2012 was basically kind of a rogue experiment where they dumped 100 tons of iron sulfate in the Pacific. And they did see a huge algae bloom, a phytoplankton bloom. But it turns out that when those plankton died, they basically decomposed and the CO2 was released. And then the other thing that was controversial, that it preferred certain types of plankton, certain species, and that people thought that that would disrupt the marine ecology. So it's been controversial. Basically, no one has done experiments since 2012 to do this, but that's just one technique. All right. Another thing is just to plant a bunch of trees. And so there was a study that said that there's actually space for 9 million square kilometers of new forest that we could plant. And that would store about 200 gigatons, billion tons of carbon, which is about 25% of the extra carbon that's in the atmosphere. There's actually this project. The guy's actually originally from the Bay Area, Brian von Hertzen. He just won this X Prize this year, I believe, for his Climate Foundation. And they have done actually field demonstrations of these platforms in the ocean that they would grow kelp on. So in the middle of the ocean, they would actually have this kelp growing off of these platforms. And you need nutrients. So the bottom of the ocean is nutrient rich. So that's actually why California has such a rich marine life, is because these currents, these upwelling currents, come from the bottom of the ocean and they draw nutrients up to the west coasts of North and South America. So we have very rich marine ecology. So what they would do is they'd pump these nutrients up and they would fertilize this kelp. And then this kelp could be used to feed fish, but also when this kelp sort of dies or breaks off, it falls down to the bottom of the ocean. And it turns out, apparently, I didn't know this, but a good amount of the oil that we have comes from old kelp that has then fallen to the bottom of the ocean hundreds of millions of years ago, that is now the oil. So this is one technique to suck up CO2 and have it sequestered at the bottom of the ocean. Then I talked about direct carbon removal, the direct capture. And so this is actually a company, this is a demonstration by a company out of Switzerland. And they have these machines with this material that's reactive to CO2. And it will actually bind with the CO2, and then when you heat it up, it releases the CO2. So by passing air through here, they can actually just suck. I mean, it's only 400 parts per million, so it's very, very dilute. But they believe it'll work, and unfortunately, we need to suck the carbon out of the atmosphere at some point, whether it's through all of those other techniques or this one. But it's expensive. It's $250 to $600 a ton of CO2 versus $50 a ton for planting trees. But they're bringing the price down. There's a number of companies that are doing this. So this is one demonstration of this. So if you just take it, if the direct air capture, if you just take regular air and you suck the CO2 out, it's very dilute. But what if you took the exhaust of a coal-fired power plant and you ran this machine off of it where the flue gas is rich with CO2, then you capture it, and then you can either pump it down into the atmosphere, into the ground where it combines with the rocks, or you can use it for enhanced oil recovery. So this is a oil well, and if you liquefy the CO2, it actually becomes a good solvent. So you could actually, at high pressures, you could actually dissolve out the oil and bring it back up. So that's one use of it. Okay. Another technique to capture and sequester the CO2 is what's called enhanced rock weathering. So rocks, certain types of rocks will naturally absorb CO2. But what if you took those rocks and you ground them up so you had lots of surface area and you spread it over fields, that you could sequester a lot of carbon? And so what they're talking about is 50 tons of ground up basalt power per hectare per year. That's a lot of rock. You could sequester 1.1 billion tons of CO2, which we're emitting worldwide. We're emitting 40 billion tons of CO2, so it's 1/40th of what we're emitting. But that is one technique that people are seriously considering. This is the ICE 911 project. So these are these microspheres that you can see. They're 35 microns in diameter. They're hollow. So they actually will float on top of any water that's on these Arctic ice. And so the person who's leading this is Leslie Field. She's lives in the Bay Area. And so they've done these tests on ice-covered lakes, and they've noticed that the ice gets thicker by putting this up. they're saying that it would take $300 million to produce the material to cover almost 10,000 square miles of the Arctic. All right. So now I'm going to get back into the basically the reflecting sunlight back in space, not taking CO2 out. So our team really doesn't like the the concept of using this, deploying this, because it's not taking CO2 out of the atmosphere. And that CO2 is dissolving into the oceans, making the oceans more acidic, which is affecting the marine life in the oceans. So this is kind of a last resort to basically cool the planet, but it doesn't suck CO2 out of the atmosphere. All right. So there's stratospheric aerosols and there's marine cloud brightening. So these are the two techniques. This is sort of a summary of what these techniques do. With the stratospheric aerosols, you would put somewhere between 1 and 5 million tons of these scattering particles. So you'd have to design special airplanes that would then take this material up to the stratosphere. And then these particles would then scatter the sunlight back up. They last about 2 years up there, just like volcanoes have done. And then there's the marine cloud brightening, which is where we just take ordinary seawater, which is about 3.5% salt. We filter it, and then we just spray that salt water back into the air. And that salt will the droplets of salt water will evaporate. They'll drift up into the clouds. Then they'll absorb water, and they'll make the clouds whiter. I'll show you how that works. And the beauty of this is it only lasts a week. So after a week, all of those particles then just rain out or drift back into the ocean. So, with the stratospheric aerosol, you're committed to 2 years after releasing anything. Store 205 gigatons of carbon. That's actually for planting trees. And I think that's over maybe 100 years, because what we've put into the atmosphere is about 1,000 gigatons of extra CO2 in the atmosphere. So this would take out like 20% of that over maybe 100 years, the time that it takes for the trees to grow. So, all right. So with the stratospheric aerosols, that's putting these particles up. So you could put sulfur up there. Now the problem with sulfur is it actually has been shown to react with ozone. And, as you all know, we had a problem with the ozone. We had these holes in the ozone when people were spraying those hairsprays with the chlorinated fluorocarbons, CFCs, and then we banned CFCs, and so the ozone came back. But the ozone at ground level causes asthma and health effects. But up in the stratosphere, it actually absorbs UV radiation. So it protects us from getting skin cancer and cataracts and things like that. So, so we need that ozone up there. But there's some thoughts that the sulfur could deplete the ozone layer. So now they're looking at other materials like calcium carbonate, which is basically limestone, up in the atmosphere. And it's a more inert material. Some people say they would enhance plant growth because it scatters the light more. The cost actually isn't that high to do it, even though you're talking about that many millions of tons every year. And we have proof with the volcanoes that it's likely to work. But modeling shows that if you do this, and depending on where you put the aerosol, stratospheric aerosols, whether you do it in the tropics, or if you do it on the poles, you get different rain patterns. So you could affect some rain patterns. So if you get it wrong, if your modeling is not very good, you're kind of stuck with it for 2 years. So, but this shows, this is David Keith. This is mostly a team at Harvard, David Keith. Our team actually helped them develop the sprayer that would spray calcium carbonate instead of sulfur. But here, this red line is business as usual. If we don't do anything, the global temperature, will go up to 1.2 degrees Celsius of an increase. If you start putting 3 megatons of sulfur dioxide in the Arctic, and this is the Arctic, you get this much less heating. If you did it in the tropical, and you did 5 million tons, you'd get this much cooling. And then if you did 10 million tons, you'd get a lot of cooling. So you actually could counteract all of the extra temperature rise. The problem is, as soon as you turn it off, the CO2 is still there. So the CO2 is still going to continue to do that greenhouse effect and trap the heat from the sun. So the temperatures will rise quickly afterwards. This is their field experiment that they were going to do. So they were going to spray this calcium carbonate up there only like less than 2 kilograms, probably about 1 kilogram, so 2 pounds of calcium carbonate. And they were going to spray it. And then it's about a 100 meters wide spray, and it's going to go for about 1 kilometer. And then they would fly this thing in like an S pattern to sample how the reflectivity of the sun is occurring, and the particle concentrations and all of that, and how the particles mix in the atmosphere. They were going to do this balloon experiment. It was going to be last year, but it was canceled due to opposition by some of the Sami people up in Sweden. And apparently the Harvard team had not done enough outreach to the native people there, so they came out against it. So they're trying to redo their outreach efforts. But the first test wasn't actually going to release any particles. It was just going to test all this equipment, because it's all brand new equipment, to see if they could actually fly in the conditions up in the stratosphere and make their S patterns and so on. So now the marine cloud brightening is the project that I'm working on. It was actually conceived in 1990 by John Latham, who said that we could make these clouds brighter. And it would basically, reflect the sunlight and cool the earth. Turns out 25% of the oceans are covered with these marine, they're called boundary layers because there's under 1,000 meters. So they're not these very high clouds. And so right now, these marine clouds are very thin clouds. They don't have a lot of reflectivity. And so if we could somehow increase the reflectivity of all these clouds by 6%, you could change the Earth's albedo on the average albedo, that's the reflectivity, by 1%, and that could counteract the global warming. So the elementary cloud physics behind this is that all of the clouds that you see are basically formed around condensing around a piece of dust, a particle. And it could be salt, it could be sulfate, it could be black carbon, it could be anything. Generally, if it's hygroscopic, it has an affinity to attract water. That's better. So salt and sulfates do that. And so if you get a large enough salt crystal, then it'll convert to a cloud droplet. And the beauty of that is that you emit a very small particle, but by absorbing moisture, it grows to the right size that will reflect sunlight. So you don't have to emit all of the full particle size that will then be reflecting the light. That's called sky brightening. So if you don't have the humidity, you could actually emit larger particles of salt, and that they would actually reflect the sunlight themselves without growing into larger particles by attracting water. So this is all based on what's called the Twomey effect. So if you have a certain amount of water, if you add more particles, if you have a certain amount of humidity, if you have these large particles, this is how you know, like, a cloud is going to rain. It's a dark cloud, meaning it's not reflecting a lot of sunlight. So it has a lower albedo. So these are these large particles. But if you go and introduce a lot of little particles, nucleation particles in here, the water will redistribute into these smaller particles that will actually scatter light more effectively. So that's the Twomey effect. And so so here you can see the cloud droplet concentration. So if you have, this is the number of particles per cubic centimeter. And so as you increase the number of particles, you actually increase the reflectance of light. So you can see that the reflectance increases with the number of particles. All right. So what's interesting is, how do we know that clouds get brighter if we introduce these particles? We can actually observe this from satellites. And what these are called ship tracks. These are cargo ships that are burning this bunker fuel, which is 5% sulfur, as they cross the oceans. And those sulfur particles then become cloud condensation nuclei, and they actually make these clouds brighter. So we've seen observations of the sulfur particles brightening clouds. All right. So if you applied it to 10 to 30% of marine clouds, you might be able to offset the doubling of CO2. So this is the warming that you get from CO2. If you cover 5% of the surface area with these cloud condensation nuclei, you get cooling. The temperature of the planet cools. And so you can counteract the doubling of CO2 by increasing the droplet concentrations, or reducing the cloud drop size, and increasing the amount of area covered by clouds. All right. So this project that follows about 20 years of theoretical modeling, and the challenge is, how do you make the right size particles? If the salt particles are too small, they won't attract enough water to reflect sunlight. If they're too big, they create droplets that are too big, and they just fall out. They're too heavy and they just rain out. So you want these particles, these cloud droplets, to last a long time. You want those very bright clouds. So they need to be the right size. And so, can we make the right size particles? So they had a conference in 2008. It was sponsored by basically the Bill Gates Fund for Innovative Climate and Energy Research. And so they thought that they would do kind of a startup type activity in Silicon Valley. And they found this guy, Armand Neukermans. And so Armand, I work with him on this project. He's really sort of the brainchild of this whole project. And he has a PhD in applied physics from Stanford. He was on the team that invented the inkjet printer. So they're really good at spraying very small particles, which is the droplets that they need for inkjet printers. So the Bill Gates team, they recruited him to start this. So they started in the spring of 2009, and Bill Gates gave a small amount of money to the effort, but it became controversial because it's weather modification. So he stopped funding the project. And then it's been basically self-funded. So Armand, we operate on a really shoestring budget. Nobody's paid. I mean, I've been on it for 10 years. I haven't been paid. So we beg and borrow whatever materials or equipment we can get to work on this. And so the task was to develop a prototype of a sprayer that would create the right size particles. It's still not clear what the right size particles are. Originally, I think it was 40 to 80 nanometers. Some people say we can go up to 300 nanometers. We actually need to do some more experiments to figure out what the right size is. And we need about 10 to the 15 nuclei per second to really brighten the clouds. So the goal was to create a sprayer that created the right size particles and that could be put on a ship to operate over the oceans. All right. So the first thing the team started was they just started a really small hole, and they tried to spray through this half micron hole, and then they tried a 9 micron radius. They started with a half micron hole, and they sprayed particles that were actually of a 9 micron radius. Okay, for the toner. And so this is the distribution. You want to have a narrow distribution of particles in the right size, because particles that are too small, they will not scatter light. Particles that are too big will drop out quickly. So they started with a half micron hole, and making the hole is not a problem. And getting the right size particles was really easy. The problem is the holes kept clogging up, so they could never design a filter that was good enough that would keep a half a micron hole open. So that was jettisoned. Then they worked on, this is before I joined the project, a thing called Taylor cones, where you have like a hole and you apply an electric field and you draw the fluid out through the hole. We worked on that for a while, and it was, you would need 10 to the 8 of these holes, and it was logistically a hard problem to create that many holes. So the latest project that we're on is what's called effervescent spraying. And this is where we mix gas and water in together, and we create sort of this two-phase flow out of a nozzle, and you can get pretty good narrow particle sizes out of this. A lot of this stuff is done, this atomization work is done for fuel injectors, because they want to create very fine particles of diesel or combustible fuels for engines. So this is our sprayer, our first sprayer, the effervescent, and we'd create about 3 trillion drops per second. And so we need about 1,000 of these nozzles to make a full sprayer to get us to 10 to the 15. And so one of the big challenges is that none of us were very good at. These particles are so small, you can't see them with your eye. I mean, they're way below the visible light. So the first way that we tried to observe them was we would try to electrostatically precipitate them out onto a wafer. a silicon wafer, and then we put them under an electron microscope, and we'd go try to measure the particle sizes. But it turns out it's very difficult to get the full particle distribution out of doing that because your field of view is so small. So then we moved on to these these specialized pieces of equipment that are used to measure air pollution, scanning mobility particle sizers, and aerodynamic particle sizers. They have different ranges that they could see. So we use both instruments to cover the full range. And so we're looking for all of our particles to be sort of in this range of less than 300 nanometers, which is invisible to our eyes. So becoming experts at this equipment is very difficult. So this shows from a 125 micron nozzle with 3.2% salt at 84 atmospheres, high pressure. You can get a distribution right here, peaking at about 80 nanometers. So this just shows the results. This is another spray that we did where we were at about 30 nanometers. So here's another distribution of our nuclei using. And so what we'd do is we'd take one of these snow makers, which are basically sprayers, and we'd modify them with our nozzles, and we would then use those to spray into the atmosphere. So we've been working on this effervescent spray for about 5 years now. We still don't have the perfect nozzle, but we discovered this other technique that actually the Dutch have been using to try to improve gas turbines for airplanes and for power generation, where they want to inject basically water vapor into the engine to make it more efficient to cool the inlet gases. And you would actually get a power increase of 15% if you could do it, and you'd reduce the nitrous oxide production from burning of the fuel. And you could actually create close to our 10 to the 15 target. And so you could get the droplets. So this is the droplets of water, not the salt crystals. So the salt crystals, we want to be in the range of, again, it's unclear, 40 to 400 nanometers. But when you add the moisture, they grow by a factor of 4 in their diameter. You know, if this works, we've just started working on this maybe a year ago. It would be much more efficient than 1,000 sprayers. It turns out that the Russians have been working on this for a long time, where they basically take water and they superheat it to about 250 degrees Celsius, and they spray it out through a nozzle. And the Russians have been working on this. The problem with it is that I think the reason why they haven't perfected it is because they're trying to use it for gas turbines. And if you have a droplet of water hit a gas turbine, it's going to break the blade. So they can't tolerate any of the larger droplets, where we can for cloud studies. So there's lots of applications for this. I'm just wrapping up here. I'm almost done. So again, the main thing that we want to do with our sprayer is to allow scientists to study what happens with these aerosols in the atmosphere. Again, the biggest uncertainty in radiative forcing was the aerosols and the interaction with clouds. So if we could provide them with a tool that would generate a lot of particles at exactly precise sizes, then they could do a lot of cloud studies. But you know, if you actually were to deploy this, you could cool the coral reefs. You could actually maybe decrease hurricane intensity, because hurricanes get their strength from the water being super hot. So, but we're losing our fog on the California coast. So perhaps you could increase clouds and increase the fog. So the Great Barrier Reef, the northern part, which is warmer, is like 81% severely bleached. This is from a few years ago. We're now in another major bleaching event. And the middle part was 30% severely bleached, and the bottom part, which is cooler, was only 1% severely bleached. So you have all these hurricanes in the Gulf of Mexico. Perhaps if you could cool the water, you could reduce the number of hurricanes. The Australians have actually taken our nozzle design and they've built a sprayer, and they're spraying off the ships, the one ship, to look at what the particles do in the atmosphere. So now I talked about the Harvard experiment where they were going to do this little balloon experiment with 1 to 2 kilograms of either calcium carbonate or sulfur, and they got shut down. But some people think of it as, well, the military could use this for weather modification and change weather patterns. So there's some concern there. You could potentially change precipitation patterns and cause droughts and floods. So you have to have international agreements. You have to have oversight. I mean, there have been rogue people where they dumped 100 tons of iron sulfate in the ocean. And there's opposition. There's people that are monitoring all of the geoengineering efforts. And again, we're not talking about deployment. We're talking about research. We've been working on this for 14 years and we still don't have a final design. We still don't understand the cloud physics. We still don't understand the coalescence of these particles when they're in the atmosphere and how they interact. And so if we don't have that information, we don't know how we're going to deploy if we ever have to. But we don't want to get to a point where we're in such desperate straits that somebody's going to just go do it without having done the research. Funding has been very difficult. As I said, we have been sort of self-funding for the 12 years for our project. The Australians are putting in about $100 million to save the Great Barrier Reef. It's a $6 billion tourism industry that they want to make sure that they preserve. So they're trying to breed corals to be more heat tolerant. They're doing that spray. There's a group that we work with. It's actually, we get some of our funding from them, but they're mainly in the business of lobbying for geoengineering research and funding for geoengineering research. So the National Academies of Science really recently published a report developing a research agenda and research governance. Governance is very key to getting this done, to reflect sunlight to cool the earth. And that's it. So I hope that is not too fast or too confusing. We really consider this to be an insurance policy, that you should have the research in your back pocket in case you have to do something, and you want to make sure that you have researched all of the different consequences of this, that your computer models are really good. Silver Lining, this NGO, they just got a huge amount of grant money from Amazon to use their compute services to do climate modeling. Climate modeling is really hard to do because you're modeling particle, it's a scale issue, right? You're modeling particles that are 50 nanometers in size, but clouds are on the order of kilometers. So how do you get a computer model that handles those two different scales? It's very difficult, very compute intensive. Okay.
I
I don't
guess
see
we
any
can open it up
questions.
for questions then.
Yeah.
Okay. I noticed that the modeling does seem to be a problem. I noticed from one of your models, I forget what exactly the effect you were monitoring, but there's an effect on global cooling and observed and modeled, and the observed cooling was much more effective than the model. So apparently there's a lot of work to be done on that yet.
Yeah, that was the Pinatubo study. Let me see if I can find it. Tubo. It was very early.
More slides than I remember.
There, this one. Okay. Yeah,
Yes,
so you
yes,
have
the
the
top one.
modeling, and then you have, and so here you can see how the model and the observation diverges dramatically in the stratosphere, right? So,
It's a very, very complex system we got here.
yeah.
When they talked about fertilizing the oceans to increase plankton, I suppose that's got to be well controlled, because you keep hearing about algae blooms that are starving the fish.
That's exactly right. So what happens is that when you get these algae blooms, you actually will take up oxygen as well. And so you can get areas that are very low on oxygen levels and the fish die. So that's a common problem in lakes and streams, where you get these algae blooms that kill all the fish.
Yeah. Michael, I see you've got your hand up.
Yeah. So I have a big picture question. So first, thank you for this presentation. It's very interesting. But if you had to choose maybe not one, but 2 or 3 most cost-effective technologies for carbon removal, so what would be in this mix?
For carbon removal,
Yeah.
well, the first thing I would do is the safest things, which is plant a lot of trees. And then for carbon removal, we're already spending a fair amount of research money on the direct air capture. And I think that direct air capture will eventually become cheap enough. What they're actually looking at is, you have this chemical called amines or amines, and they absorb CO2, but then you have to heat it up to release the CO2. So they're actually building a demonstration project in Reykjavik in Iceland, where they have extra heat. And they're also looking at the excess heat from power plants to be able to extract the CO2 from the amine solutions. So you might be able to do it for a lot cheaper if you're using waste heat. So I'd say those are kind of the 2 more promising things. The other stuff is really controversial. I mean, ocean fertilization would be incredibly inexpensive, but we don't even know what the full impacts of it are. It's very hard to model the whole ocean and all of the life forms in the ocean. I mean, I think when they did the ocean fertilization, they sort of preferentially grew one type of plankton, which may not be the food source for a lot of other types of marine life. So it's kind of scary.
Ray.
Okay, I've got a question on what your crystal ball says. You've been in research now for 14 years, and we've got, 10 years, or depending on who you talk to, some amount of time before we have to start making a real difference. Do you think that your research is going to be at a point where this can be deployed soon enough to make a difference when we need it?
I always refer to what we did in World War II, when you basically shut down the whole economy and created millions of tanks and millions of guns and hundreds of thousands of airplanes. I mean, you could pretty much do anything you wanted if it was an emergency, right? But people would have to sacrifice a lot, like they did in World War II, where you had, rationing of everything. But again, we don't have the research, and research takes time. And so we need the funding for the research. The very first thing we need to do is and the cheapest thing to do is stop emitting carbon. I mean, that's the most obvious thing. Just stop emitting carbon. And this is what I say, is that if you buy any appliance right now that uses fossil fuels, you're committed to another 15 years of burning fossil fuels. If you buy a fossil fuel water heater, 15 years of burning natural gas. So that's why I'm encouraging everyone to get heat pump water heaters, induction stoves, heat pump furnaces, electric cars. Do not burn fossil fuels.
Yeah, I agree that we need to stop emitting carbon. Personally, my advocation is for nuclear energy, which is probably one of the quicker ways to replace fossil fuel burning for energy.
Yeah, so I mean, I'm all for extending like Diablo Canyon, but the problem is it takes 10 years to get a community to accept a nuclear power plant. Then it takes 10 years to build one of the large 1 or 2 gigawatt power plants. We don't have 20 years. Now, the modular power plants, none of them is in full production. I think there's maybe 2 in China right now, but none of them are in production. None of them have been qualified by the NRC. So it's like, are we going to have them in time?
I think China does have one small modular reactor in production, and they are building reactors very fast. And I think that we could, if we wanted to, change our approval process to make it much faster.
No,
and all these other things. I agree that we need a war effort kind of approach to solving climate change.
we do. The problem is China can just say, you're going to put one here. We can't do that. I mean, I'm an elected official. Everything goes through a huge public process to do anything. And you have a lot, I mean, just for housing, we have a lot of NIMBYs are not in my backyard. Where are you going to put these nuclear power plants?
Yeah, without changing anything, the US can't contribute much to solving climate change.
Well, we can. We're doing a lot of research on lots of things. But in terms of nuclear, and we had these thorium reactors, right? And we've been the leaders in nuclear for a long time, but it's just so hard and so expensive to do nuclear in the US.
Okay, Gary, or Jerry, excuse me, or Dana.
Hi, yeah, I had a question about, you said that algae blooms that were using up oxygen. I thought blue-green algae produced oxygen when the Earth kind of changed over from a methane atmosphere to an oxygen atmosphere that was done by huge amounts of blue-green algae.
You're right. And you're beyond I'm not a biologist. I don't really understand it, but I know that you have these fish kills when you do get these algae blooms. And so my understanding is like plants will take up CO2 in the day, but they actually take up oxygen at night. So I'm not sure exactly how it works. I'm sorry.
Okay, thank you.
Yeah. What are the idea of glass beads and the over the seas to reflect light? Have they looked into what effect that has on the animal life there? Can the fish
They
eat
have.
beads? And
They've actually, unfortunately, they've fed them to birds.
ah,
And uh, it's a silicate. It's just like sand. It's just like a bird eating sand, I guess. I don't think that they've seen any negative effects. It's just the issue is, these things are super light. Are they just gonna, like, with the winds in the Arctic are fierce? Is it just gonna blow all this stuff off of the ice into the ocean, where it probably won't? I mean, they do float. So, but I think they'll probably be covered with algae soon. The problem is it's very hard to do a field experiment
yeah,
because you don't know the consequences, but you have to do the field experiment. So
we,
I don't
we need
know.
another planet to experiment on.
Yeah.
The other question I had about
Maybe that's why Elon wants to go to Mars.
yes, but if you can't keep Earth terraformed, you're not going to have much of success on Mars. I was wondering also if when you talk about increasing reflectiveness of the clouds and so on, does that have any effect on the plant life? I mean, if there's less energy reaching the
Yeah,
forest in the field, is that
yeah. So this was actually one of the things that is here is one of the advantages of stratospheric aerosols. Some people have said, and we haven't really modeled it, is that it could enhance plant growth, because what it does is it scatters the light so that directly below the sun you'd get, you're reducing the radiation that's hitting the earth, so it would get dimmer. Okay. But because it scatters light to other parts, I think the days might get a little bit longer. I'm not exactly sure, but the problem is that when the temperatures get hot, plants actually produce less food, because if you think of corn, the corn has this silk, and every silk thread goes to a grain of corn, a kernel, and the pollen is transported through that silk to the kernel. But if it gets really hot, that silk dries out before the pollen can get transported. So you actually, above certain temperatures, you actually look at reduced crop yields with higher temperatures. And Lester Brown has done a lot of work on this, and he says that I think above 30 degrees C, you get dramatic reductions in crop yields. So you have the temperature effect, and then you have the sunlight effect.
I see. Matt, you're muted.
There, should be unmuted now. So I have questions about, I know this is not your focus, Suds, but the, what was it, the basalt one?
Yeah.
Version where it's actually using it to suck CO2 directly out of the air. I don't know, there's another project I've been following that doesn't use basalt, but does something very similar. It's called Project Vesta. I don't know if you've heard of that one.
No.
They're using olivine.
Oh, yes, I've heard of olivine. Yes.
Yeah.
Yeah.
Yeah. I guess there's several of them doing. They're specifically putting it in like active beaches or active coasts to allow the waves to weather it and pull out the CO2. I didn't know if you had anything anything to add about that. It seems to work similarly, but it's not. It looks like the basalt pulls out a lot more because the olivine, it's about 1 ton of olivine pulls out 1 ton of CO2 approximately.
Yeah, I'm not an expert in this.
Yeah.
I was just kind of trying to, my area is the marine cloud brightening, but I just wanted to give you guys a flavor of all of the different stopgap measures that people are trying to do out there. We need to be very creative.
Yeah. Fair enough. It just seemed like doing these different kind of sprays and stuff have not been, the research isn't quite there yet. We're not ready for prime time, and it's almost late to have a stopgap method or something.
Well, the funding has been really hard. I'll just explain
Yeah.
what happened with Bill Gates was he gave our project before I joined about $300,000. And
Wow.
then there was some negative press about how he was funding rogue scientists in Silicon Valley.
But can
And
I
his
ask?
people came to,
Can I ask if the negative press had to do with like chemtrails or something?
just I'm not exactly sure, but the chemtrail people are definitely involved. Yeah.
Yeah. Okay.
And so the thing was that his people basically told him, it's like, look, you're trying to solve malaria and all these health problems. Do you want to get involved with something this controversial? I mean, as it is with the COVID vaccine, everyone thinks Bill Gates is putting a chip in your arm. So he is funding the stratospheric aerosol stuff, the Harvard team, but he hasn't funded our team in probably 15 years, 13 years, just because of the controversy. People go after him for all kinds of things.
Yeah.
So Suds, did you have a fund me project?
I actually have been telling the team we should do a fund me, but they haven't really warmed up to that idea. So
But tell them I said it was a good idea.
okay.
Um,
Money is starting to flow. Like I said, the National Academies is now pushing for funding. And so it turns out that, and the Australians, we actually want to try to apply to the Australians to get some of their funding. But so far, our team has been just retired engineers and scientists, just working on our own time to do this stuff. We're now working with Palo Alto Research Center, Park, and so they actually have staff that are funded to do some of this spray research. So the money's coming, but when you think about the scale of it, there should be tens of millions of dollars in this, but there isn't. And so a lot of it is coming from private, like, philanthropists that are starting to fund the efforts. So we're starting to see some philanthropy money coming in.
okay. Jerry or Dana, and you're muted. You're still muted.
One of the things I remember from a climate science class is that if the planet heats up, what will happen to the cloud formations around the world is uncertain.
Yes.
And that, what effect does that have on your brightening clouds calculation?
Again, the cloud aerosol stuff is really not well understood. We need to put money into the research, because water vapor is a huge global warming component. It traps a lot of heat. And so if you heat up the planet, you will increase evaporation. So you might get more clouds, which could act to cool the planet. But again, it's really unclear which way it's going to go. So we know that from the Twomey effect, if we add more nuclei to dark clouds, we can brighten them. So, so we're kind of betting on that. And then there are areas of the ocean that have plenty of moisture, especially on the west coasts of continents. So what happens is all the dust from China is kind of filtered out as it crosses the Pacific Ocean. So the air hitting California is pretty clean. It doesn't have a lot of dust or condensation nuclei. So the west coasts of continents are more ripe for marine cloud brightening because you're lacking condensation nuclei.
Yeah, I was kind of wondering also about when you were talking about narrowing the distribution on the size of the drops when you do the seeding. You said that if they're too large, they just drop out and have no effect on reflectivity. But I'm wondering if your distribution is wide, is that a problem with what remains? I mean, do you treat the amount of moisture in the air as basically a constant? Or
yeah, pretty much. So what happens is when we introduce large particles, they will pull a lot of moisture out and they'll rain out. And that will decrease the amount of moisture in the air. So they're very negative to what we're trying to do. So we're trying to perfect our sprayer such that we emit hardly any large droplets.
It's not just that they're ineffective, they're actually harmful.
They are harmful.
Okay. I guess the other thing I was wondering about when you talked about basalt and what was the other thing? Calcium sulfide, is that a limited resource?
Basalt is not a limited resource. We actually have lots of it, but it's a really hard rock. It's the rock that's igneous rock. You know, so often it's deep. I honestly don't know where it's distributed. I'm not a geologist. And the calcium carbonate is limestone. And we use calcium carbonate for everything. We use it for making cement. All the cement is made from limestone. So you can think of how many millions of billions of tons of limestone there is, or cement that we're using.
Yeah. I guess a question I often occurs to me in these discussions is how bad can it get? You know, if we continue on our present course until it was impossible to run factories anymore, just would we turn into Venus?
So there are in the climate models, there are 3 stable states for the planet. One is an ice planet where somehow a global winter event, you know, a nuclear winter event or something, cooled the planet enough that you got so much ice that it reflected so much sunlight that you never recover from that. You just are stuck in an ice planet. There's another stable state, which is a all water planet where there's no ice. And then sea levels will be like 100 meters higher than they are now. And you basically can't get out of that because you don't have the ice to reflect back the sunlight. And then there's the medium zone that we're in. So it could go any of those ways. We know that historically we have a long way to go because from the paleoclimate data, we know the planet has been much hotter and much higher levels of CO2 than we have now. But, you know, all of our big cities are on coasts. They'd all be flooded. You'd have a huge humanitarian crisis of moving all those people. wars and famines and who knows.
I suppose another problem is we don't know what new pollutants will come up with in the future.
Yeah.
And even if we got it under control, it's not clear that the climate would settle back to what it has been in the past. There may be variations that disrupt the food production.
Mhm. Well, this is why I'm working on it, because I'm pretty scared for kids and grandkids.
Yeah.
I think we need
You
to
guys want-
continue to do research so that as things change, we'll have the technology to do what we need to do.
We'll have the technology, but also the understanding. Like I showed you, it depends from the David Keith stuff. It depends on where you release the stratospheric aerosols. If you release them in the Arctic or in the tropics, you have a very different effect. So we need the research to know how much to do and where to do it.
Yeah, I think that's what I meant to say is we need the knowledge.
Yeah.
Dana, Jerry.
It's Dana, and I just have a kind of comment to make, which is it's kind of amazing that here in Silicon Valley anyway, there's this really profound, almost religious belief that technology is going to save us from the fate that's been brought to us by technology. And it's just so unbelievable that people knowing about all this stuff, and I'm sure many do, and I would suggest they read Kim Stanley Robinson's Ministry of the Future if they want to get really scared. And that hardly anybody does anything about it. Everyone's still driving gasoline powered cars, still using fossil fuels and so on. It's still traveling on airplanes. And I don't think that many people have changed their behavior that much.
That is a very key observation. And there's a thing called the moral hazard, which is if we develop this technology, people are like, I don't have to do anything. I can still keep driving my car. I can still take those, airplane trips to Europe every, few times a year. I don't have to do anything. I can still burn fossil fuels because somebody's going to take care of it for me. And that is really a problem. And some people say you shouldn't be developing this technology because you're going to give people an out. But like we said, it doesn't take care of ocean acidification. We don't believe it's an out.
So it's kind of like the mutual assured destruction hypothesis. You have to really believe that it's a threat. You can't ignore it.
Yeah.
Well, even if you don't believe it's an out, there are a lot of people who are going to still think it's an out.
Especially the oil companies. Yeah.
Could we stop sharing for a while? I just want to see who else is
Yeah.
here.
Oh, yeah, of course.
I see there are a lot of people who haven't made any comment. And who is that? Oh, Jim, you're here. Okay, it sounds like no one has any suggestions for you.
We're always looking for volunteers, any retired people that want to come help us out. We actually lost one of our members last year to a heart attack.
So do you need volunteers who are familiar with the equipment you're using, or who can?
Someone who's somewhat technical, doesn't have to be like, I'm an electrical engineer. A lot of this physics that these guys talk about, the fluid dynamics, I don't even understand. but I'm able to contribute. So
Do you have to be in the area?
you do.
Did it or not?
You need people that can knobs on the equipment.
Zen,
Unless you're a fluid dynamicist, we'd love for you to do some modeling for us.
yeah, sounds like modeling is a big part of it.
Oh yeah.
Does fluid dynamics also include somebody to make the coffee or what?
Zem, you've got your hand up.
Perhaps I should unmute myself like everybody else. So thank you for the interesting talk. It seems that the different technologies you describe, including the cloud brightening, are what I would describe as mitigation strategies, right? To sort of reduce global warming somehow. I'm beginning to suspect that the time for mitigation is over, that we lost, that climate change is here, and that what we must do is switch from, I mean, of course, it's not a binary off and on situation, but it seems that adaptation becomes more important. You know, if the water levels rise in the oceans, for example, what do we do about it? Not in terms of stopping it, because we can't, in my opinion, but how do we adapt, as a civilization to these different issues? Or do you believe that we can still mitigate things, that it's not too late, that we can, save the climate, so to speak?
Well, it's a combination of both. You have to do both. We're already doing adaptation. If you look at Miami Beach, they've spent $400 million to install pumps and to raise the roads and to add seawalls. If you look at Foster City, they did a $90 million parcel tax to raise their seawalls, I think by 4 feet. It was actually cheaper to do that than to pay the extra insurance at the insurance companies. So if you look at insurance is going it's just crazy right now. Fire insurance, everything. And so the insurance is going to drive a lot of things. A lot of people will not be insured. And I hope the federal government won't do what they're doing with all of the coastal communities and continue to insure people through FEMA that are living in places they shouldn't be living.
So government policy can be harmful, in fact, in many respects.
Oh yeah.
Jerry,
Yeah, I think if you don't do mitigation, the world is going to be so awful. There's no adaptation possible. Partly because of sea level rise, partly because you won't be able to produce as much food. So you're going to have massive famines. You're going to have massive migrations. It's just going to be so awful. I mean, forget it. You get, I believe that $1 spent on, even now, $1 spent on mitigation is worth many dollars on adaptation.
Absolutely. Building those seawalls are very expensive. And
So I'm another electrical engineer.
All that lost real estate. Yeah.
Yeah, I'm another electrical engineer, and I think that, really we need to work on all of the above, and there's going to be different people, different groups that are working on different aspects of the overall climate problem, and hopefully we get it together enough to solve it.
Well, I hope I didn't depress you guys.
well,
I
it's
think
nice to see that work is being done on all fronts.
I pay attention to climate change all the time. It's been a large part of my life for at least a decade. And you're not adding to my depression. I've already got it. You couldn't do much to it.
I know that's where you stand, Jerry, because I see your emails. Yeah.
Is it too late to save Greenland? And
it's hard to say. The models are not exactly perfect. You know, you just keep waiting for some big ice sheet to fall off of Antarctica and you know, cause really crazy things. But maybe, like I said, if you need a war effort, you got to wake people up.
The world is more dangerous too. I mean, 20 years ago, we weren't aware of all these big rocks flying around the solar system close to the Earth. So,
I think maybe what we need is to start World War III, not against each other, but against climate change.
Absolutely. That's what we need.
Yeah, but the question was just raised, how do we get the people to wake up so that that can happen?
Yeah. That's the whole thing about that movie Don't Look Up. If you guys haven't seen it, you have to
I
see
saw it. I loved it. I was about to ask you if you'd seen it. Yes, that was
yeah.
very good.
Yeah, it's a very good movie.
Too long, but what? For such a short message.
So some people think, look, if you wanted to talk about climate change, the movie should have been about climate change. But I can't imagine how you could do a decent movie about climate change. No, I think what they did was just right. And anybody who's concerned about climate scientists, they knew what it was about.
Yeah.
Senator just recommended that you could write letters to the editor to bring the problem, you know, make the problem more apparent to the people in the area.
Well, CCL's been doing that all along.
I did get one published in Metro on Earth Day about climate change. So yes, they are looking for letters of that type, I think.
I should have read it.
You want to?
You just did it.
Okay. Well, we seem to be slowing down here.
Okay.
Any last comments? All is
think
not
I'll-
lost.
I think I'll say goodbye and thanks, Suds, for a great talk and
Yep.
enjoyed it and a lot of food for thought.
Matt,
Okay, related but not exactly on topic, but Suds, you said you had an electric car. I bought my electric car recently. And for anybody who does not have an electric car, I want to point out one of the big advantages, as been said a lot of times, is the power, you know, the cost of electricity and everything. But what people don't realize, and I found out recently, is even if you're on, you know, high carbon electricity, you're still saving a lot of carbon. And the reason has to do with the size of the battery. So I have a Tesla Model Y, particularly specifically the long range version, and it has a battery that's 75 kilowatt hours. If you compare that to the amount of energy in a gallon of gas has about 33 kilowatt hours, which means when I fill up my car with electricity, fully charge it, I have the equivalent of about 2.5 gallons of gasoline power in it, which is why it's way cheaper to run and saves, you know, CO2, because it's just not using as much power as, or wasting energy on burning gas. So if you can do it, I know electric cars are more expensive, but yeah, if you can afford an electric car, get one.
Not all electric cars. We have a Fiat 500. We paid roughly between 8,000 and 9,000 for it used.
Nice.
Had it since 2015, an electric car, and that is partly powered by our solar panels. And we have had no trouble with it. The only time we've ever taken it to a garage is to get a tail light replaced. And I have not been in a gas station since 2015. What a wonderful freedom.
I have the
Yeah.
same experience. My Ford Focus Electric was $15,000 new in 2014. And I've had zero service on that except new tires.
We've had to take our Fiat to the service station twice, and both times it was from factory recalls for some kind of programming problem.